All right, this is Unit 5, Calculus, Day 40 notes. This is Part 3. So Rolle's theorem guarantees that if a function is continuous on the closed interval from a to b and differentiable on the open interval a to b, and the endpoints f of a and f of b are equal to each other, the values of the function at the endpoints f of a and f of b, then there is guaranteed to exist a value of c on the open interval a and b, which means it cannot be either a or b, which we found out in the last example where we had 0. So guaranteed to exist a value of c on the open interval a to b where the instantaneous rate of change is equal to 0. What does that stand for? That's telling us instantaneous rate of change where the derivative of the function equals 0. So we said the derivative, which is the tangent line, is the instantaneous rate of change, and the secant line is the average rate of change. Now, we're going to build off of Rolle's theorem and into the mean value theorem, MVT. Okay, and the mean value theorem is similar. In fact, Rolle's theorem is a specific case of what is known in calculus as the mean value theorem. What does mean stand for? It is average. So let's look at this theorem. All right, so let's talk about the mean value theorem, and then we'll see if we can come up with a quick example of it and talk about what it means. So now the mean value theorem again, which is the average. Up above Rolle's theorem, we're talking about instantaneous rate of change. So now the mean value theorem, MVT, if f of x, the function f of x is continuous on the closed interval a to b and differentiable on the open interval a to b, just like Rolle's theorem, but now we're going to guarantee that a value of c exists on that open interval such that f prime of c is equal to f of a minus f of b all over a minus b. Hopefully this looks familiar. And again, if here's my a and there's my b, and I have any function here, what we're saying is that, again, f of a and f of b, hey, that's the y value of these two endpoints. A minus b are the x values. Hey, we're trying to say that the slope of this secant line is going to have some value. This slope might be exactly equal to the slope of the tangent line here. Now again, in this case, my example, there might be a couple different places where the tangent line can equal that slope of that secant line. But again, what's the secant line? Average rate of change. Tangent line, which is what we're doing up above, we're saying the tangent must equal 0, then that's instantaneous rate of change is equal to 0. Here we're saying, hey, the secant, there's got to be a tangent that not equal to 0, but is going to be equal to whatever the secant line is. And again, what is the slope of the secant line? Change in y over change in x. That's this fa minus fb all over a minus b. Okay, so let's try this first example. All right, so consider the function h of x equals 3 minus 5 over x. It's pictured right here. Does the mean value theorem apply on the interval from -1 to 5? So here's -1, here's 5. Okay, so one of the things we're going to find out is that it from -1 to 5, first of all, I look and I see, hey, where is this function undefined? Well, when x equals 0, it's going to be undefined. So that's within this interval. So therefore, the function h of x is not continuous at x equals 0. Therefore, the mean value theorem is not applicable on the interval from -1 to -5. Right on -1 to +5. Okay, so again, first thing is it has to be continuous. From -1 to 5, it's not continuous. All right, the next one says, well, hey, let's double check a different interval. So from 1 to 5, well, I know it's continuous from 1 to 5. I know it's differentiable from 1 to 5, and that's all we need for the mean value theorem. So yes, that's going to apply. Let me write that down. And again, it's continuous on the closed interval 1 to 5 and differentiable on the uh, open interval from 1 to 5. Therefore, the MVT is applicable. And what's this going to look like? Let's just quickly give a sketch, and I'll come back and erase it before I go to the next one. So here, if I had to do this, here's my secant line. And actually, they're going to ask us to do this on the next one. So there's a secant line, and what we're saying is that there's going to be at least one tangent line that's going to have the same slope as that secant line. And it looks like be somewhere around there. That's not exact, but we can look at that in a second. So that's what the next one says. So graphically, what is the MVT guarantee for the function? And let's kind of put it. Let me get a better example of that. So that's a better example of the line. So a value of x equals c, where the tangent line drawn to h of x is parallel to the secant line. Again, what does it mean to be parallel? It means their slopes are equal, passing through the endpoints of the interval 1, -2, and 5, 2. Okay, so there's my secant line, and that roughly is going to be where the tangent line is. And now let's find that. This last step is let's actually find that value of c using um, using the mean value theorem. So let's go back up to what the mean value theorem. I have to show that the derivative when x equals c equals f of a minus f of b all over a minus b. Now we're not doing f of x, we're doing h of x. So I know h of x is equal to 3 minus 5 over x, which I'm going to write that as 3 minus 5 x to the negative first, because it's going to be a little bit easier to take the derivative of that. Derivative of 3 is 0. Derivative of negative 5x to the negative first is going to be 5x to the negative second, and that's going to be equal to 5 over x squared. Okay, so we said the derivative, instead of f of x, f prime of x, it's going to be f prime of c. So now we're going to say, again, we're trying to show that h prime of c equals h of a minus h of b all over a minus b. So this is going to be 5 over c squared. It's going to be equal to h of 1. So when I let x equal 1, it's going to be 5 over 1 is 5. 3 minus 5 is -2. So h equal 5. 5 minus 5, 5 divided by 5 is 1. 3 minus 1 is 2. So -2 minus 2. And then 1 minus 5 is -4. So I get 5 over c squared equals -4 over -4, which is going to end up being 1. 5 over c squared equals +1. Let's multiply both sides by c squared. So c squared equals 5. Square root, square root. And again, we're going to plus or minus. So c equals plus or minus square root of 5. Well, I'm on the interval from 1 to 5, so I know c must be equal to positive square root of 5, and that's going to be roughly 2.236. And let's see if that's where I drew my tangent line. We'll say it's right there. And that looks like it's a little bit above 2, but less than 3. So close enough. Okay, but that guarantees me that at that 2.236, or positive square root of 5, the tangent line at that point is going to have the same exact slope, or be parallel to this secant line. Okay, that's going to be it for part 3, and one more problem, or one more page on the notes.